Thank you, Michael. Can everybody hear me okay? We're good online. Right, so I often like to start with this micrograph. It's one of my favorite micrographs of all time, from Jacques Dubochet, more than 30 years ago, of adenovirus. And you can see the, extraordinary, it's an extraordinarily beautiful image. And in fact, ultimately became used for the icon of EMBL, that little symmetric thing with the green dots and whatnot. It's actually meant to represent one of these images. And if you look at this micrograph carefully, you can see both, the potential of the field once you could, prepare these specimens in a reasonable way, vitrify them, and have coherent electron sources that were good enough to actually, image secondary and tertiary structural features. You could see the viruses. You could see as the ice gets thinner, the material inside the virus got splayed out on the air-water interface. You could see the individual assemblies, these little bits of 9 subunits put together, and then even the individual subunits. So I think if you think carefully about this micrograph, you could see the potential and the power of cryo-EM, but also a lot of the problems that we are still absolutely dealing with on a daily basis, as we've heard about in other talks today. So anyway, I'm going to talk a little bit about our attempts to improve technology in cryo-EM, and in particular, developing a new microscope for single particle cryo-EM. I don't think it's any surprise to anyone that we are entering this great era in single particle cryo-EM, and we've seen different versions of these statistics in previous talks already. This is a tabulation of all of the structures in the PDB according to technique, which you can download, and you can look at the progression of the number of structures determined by X-ray, EM, and NMR. And of course, NMR peaked back in the mid-2000s and has been in steady decline, but is being used for other things now. X-ray peaked much more recently and is still going very strong with more than 10,000 structures per year, but it also is starting to be sort of redirected towards particular problems given the success of EM and in determining structures of so many things now in such a wide range of proteins. And so this last number here is today. I looked it up this morning, and this is the number that's been deposited in 2024 so far. So we're at a ratio of 1.6. So Becky is indeed correct. Possibly next year sometime this will go to parity, although there are lots and lots of structures being determined by fragment screening, as Martin told me recently today, that'll be deposited. So these statistics don't tell the whole story, of course, because you look into the details of what types of structures are being solved, and then you learn even more about how the techniques are being adapted for what they're the best at. Anyhow, we're still keen on pushing cryo-EM forward. And in particular, today I'm going to mostly talk about improvements in cryo-EM hardware for single particle, at least to start. And so the question in my mind is, this is a nice electron cryomicroscope, and it has an extraordinary amount of technological development in it. It's all hidden inside this box, but there are years, if not decades, of effort from hundreds of people to make something this extraordinary that can do the things that we do for it. But on the other hand, you can look at this and think of it as something like this. In fact, this is sort of how I see a modern, expensive 300 kV cryo-microscope these days. It's a beautiful thing. It has a lot of technology that was developed in it to do things that we don't do in cryo-EM, in single particle cryo-EM for sure. And on a day-to-day basis, it's actually really more than what you want. If you want to come home from the garden center with a Christmas tree, the Ferrari is not the thing you want to drive to do this, right? You want, you want the hatchback or the pickup truck or whatever. And so our recent efforts have been to sort of switch from these expensive built for everything microscopes to cheap purpose-built electron microscopes. And I think the surprise for us, we knew we needed cheaper microscopes because we knew in order for the field to grow, for that exponential curve to continue, that we needed to reduce the costs so that you could have more availability of microscopes for the entire community and more ability to actually solve structures on a variety of different problems. But we realized pretty quickly going into this that we could actually make the microscopes better and cheaper at the same time. And I think this was a bit of a surprise to most people. So let me explain why we think this. So the real basis for it, there's a whole series of papers we published on this, but if you were to boil it down to one slide, as I've done here, there's this paper that we published on the theory of information transfer in electron micrographs, like that one I showed at the very beginning. So forgetting about all of the other technology of the microscope, the detectors, everything else, this is just the electron scattering from the specimen itself. It turns out that there's an optimum energy for a given thickness of specimen, if it's radiation sensitive. And for the vast majority of specimens that we're doing in single particle cryo-EM, they're in something like 300 angstroms thick of ice. And it turns out that the optimum energy to be imaging in that is actually 100 keV, not 300 keV. And if you have a much thicker specimen, like you might do for an in situ type work, then you might want to have higher energies. But this is quite general, and it was based on old physical theories. But then we realized there weren't accurate measurements in this range. So this dark regions of these two curves of the electron scattering cross sections were actually measured by Matthew Pete in my group, so we became quite confident that they were very accurate, and they also matched our measurements of radiation damage. So we think this is indeed correct, and that if one were to switch from 300 kV to 100 keV for the vast majority, say more than 90% of all the structures that are being determined and put in the PDB right now, you would have something like a 30% improvement in the signal in the images, just because you don't damage them quite as much per unit contrast. So that is not something that we would give up, I think, in any serious way when we're, solving, thousands of structures per year as we are. But, theory is one thing, and actually putting this into practice is another. So we took one of our old microscopes, an F20, turned down the voltage a few years ago, put an X-ray detector on it, sort of hacked it all together. And with this flash up, in 1 week's time, we did these 5 structures, one of which was at about 3.5 angstroms or so, this TPS. So this convinced us that there were no holes in our theory, that, we hadn't missed something. There wasn't something going on here that was, hiding from us. And so we said, let's do this. Let's have, 100 kV microscope. And we, of course, went to all the microscope manufacturing companies and told them this, and not much happened, I have to say. We do what you do when you're in this situation. We said, okay, we're going to have to do this ourselves. And so this was the cartoon that we put into the grant proposal. As you also do when you write a grant proposal, you have to have a cartoon. So this was the cartoon that we wanted 100 keV power supply, a new 100 keV FEG that was designed for our work, had the amount of current and spatial coherence that was appropriate, but not more. And we want a new transfer system that's fast and simple and easy to use. Could be automated eventually, but the key thing is to be able to get a grid in and out fast and easily, and then have the best possible detector we can. And so we put together this partnership between these collaborators. This is our collaborators in York Probe Sources. This is a company that was started as a spin out from York University, run by Mohammed El Gamati. And the column, after testing lots of different columns, we settled on the Joel 1400 column, because it's a very robust, easy to maintain, very simple microscope that's also inexpensive. And it was the closest to what we wanted. And then the stage, we're in ongoing efforts to improve the specimen loading system. But for the demonstration purpose, I'm going to show you now, we used all the commercial holders that are available currently on the market for side entry systems like this. And then the detector came from Dectris, which is, of course, very famous in the X-ray community, and the dominant player in the synchrotron world, but they have been moving into the electron world as well. And so we have one of their latest detectors as well. So that's the cartoon, and this is what it actually looks like in the lab in Cambridge. Many of you here have come to visit, and that's great. We're happy to show everyone this. This is the 100 keV new power supply. It's a brand new design by the folks in York, and you can see the cable coming up to the new field emission gun here. So this is an entirely built from scratch new gun. This is the 4th prototype of it. There's going to be a 5th one coming soon to us, and hopefully that's the one that could be put into microscopes that you might buy sometime soon. And it has the benefit, when you start with a blank sheet of paper, you can get rid of things that cost a lot of money that you would otherwise have for other applications. So in this case, one of the main things that you don't need at 100 kV, which you do need if you're at 200 kV or 300 kV, is SF6, which is this, horrendous greenhouse gas, which, there are mechanisms for dealing with it, but it is expensive and it would be much better if we didn't have it. And so this gun doesn't need it, which is nice as well. So the whole thing has a couple of pumps on here and a gate valve and can be mated on top of a column. And so the other thing we changed was the lens, and I'll show you that in a second. And then here's the Dectris Singla detector, which is one of their first electron cameras that's been designed to attach to a standard electron microscope. And you can see it has a little low-dose interface here, which was written by Greg McMullen, which we use to actually collect our data sets. And it fits in a nice little room. This is only about 3 by 4 meters big, including everything. And you can see we have a manual plunging unit here, which we make, in the workshops at the LMB. And these have now been commercialized. And you can even look at your grid just after you've plunged it with a dissecting microscope, put it in the microscope column, have a look, take it back out again, and make another grid within, a short period of time, maybe 10 or 15 minutes. Usually we go for coffee and then come back and then do another one or something, like this. So if I go into more of the details of the microscope itself and what we've specifically changed here to make this thing suitable for structure determination, it's these 3 elements really. It's the high coherence 100 keV shock key electron source, which you can see at the top here. This is the gun. If you take the head off of it and look down on the top, so the electrons come out from this little hole here and then come down the column. We have a new, well, not a new, it's a lens design that already existed, but it has a lower chromatic aberration coefficient than the ones that are normally in cryomicroscopes. And that's important to reduce the effects of the coherence envelope function, the temporal coherence envelope function. So, and Joel did this, so they added a very good cryo box design here. So the gray bit here that I'm pointing at with my arrows, you guys can see this okay, yeah? Okay. That's the new cryo box, which is quite effective and still fits in this low CC lens, which has a smaller pole piece gap than the ones that are in the standard 300 keV instruments. And then this is the Dectris Singla detector, which is actually made up of 2 modules. Each is 2 by 4 ASICs put together, but they can only butt these ASICs up on 3 sides because the information has to come out somewhere in some wires. And so there's a gap down the center here, which you can see. It's a physical gap of a couple of millimeters, but then there's a full set of pixels on the other side. So altogether, this is 1K by 1K. So a lot smaller in terms of number of pixels than people are used to at 300 kV, where we have 4K by 4K 16 megapixel detectors. So this is our measurements of the performance of this system. And so I'll start from, I'll go in inverse order here, if you will. So measuring the performance of the detector, this is the detective quantum efficiency, which you can see as a function of spatial frequency. This is Nyquist, so 1/2 the sampling frequency. And you can see it's extremely good, actually. If you take, say, the theoretical performance of a perfect pixelated detector, so essentially perfect efficiency in a square pixel, it should have a DQE at Nyquist of about 0.405. And this is significantly more than that at about 0.53, which means that the information transfer here is extraordinary. And you can actually tell to a quite good degree where in the pixel the electron hit by using this additional information. And this is partly due to the very high efficiency of the detector, and also Greg's new counting algorithm, which he implemented on this to enable us to get the maximum amount of information out of each electron event. And that means that we can use this region out here into the super resolution quite effectively in structure determination, which I'll show you in a second. And that was important because we only have 1K by 1K pixels. So you don't, you can't play this trick that you play at 300 kV where you turn up the magnification in order to make up for the fact that the DQE isn't as good as you would hope it to be, which is what we all do on the current generation of 300 keV detectors. So so anyway, this really did make a big difference in the success of this. And we also measured the CC of the lens. So, you specify the CC of the lens, but you want to know it is actually measured for real. So this is actually a measured voltage of the power supply. This is the actual change in defocus as a function of energy, which then gives you the chromatic aberration coefficient. The lens is specified at 1.8 millimeters, and we measured 1.95, which when you include the CC of the projection optics, this makes sense. This then allows you to calculate an envelope function, which is this purple thing here, given the energy spread on the source, which was also measured for this gun design. And then we put in some test specimens to see how it looks in terms of an actual image. So this is a little bit of amorphous carbon on graphene, imaged at fairly high magnification, but not terribly high. You can see the 2.1 angstrom reflection very nicely coming through in the signal. This is not a super resolution micrograph, but this is. So here we've taken an image of gold on carbon, and the Nyquist frequency is this dashed circle here, which corresponds to this point here. So you can see if you integrate around the ring here, you get this nice tone ring pattern, which falls off, but goes right out into the super resolution range. And you can see the 111 and 110 rings in gold very nicely. And this was important because this is the actual magnification we used for all of the structure determinations, or just about all, save the ribosome. And so we wanted to be sure that we actually could get effective resolution well out into the super resolution range, and we could. So essentially, these measurements convinced us that the optical system here was all done correctly and was performing as we wanted. This was the case in about December a year ago. Well, a year and 4 months ago now. And so in January, we decided to start testing this thing for real. But we did put in one more little sort of lump of metal, as it were. So this is a micrograph of gold, 200, where it's been oriented along the viewing axis. You can see now the gap in the detector here, but it's been filled in by just some gray levels by Greg's nice software. And so if you zoom in on a particular region, you can very nicely see the atomic columns in the lump of gold. And this was to get the attention of the microscope manufacturers that, this is a pathology grade microscope. This thing is what you would sell to the NHS to put in their lab to look at, plastic sections that could diagnose kidney disease or something. But you can see atoms with it, right? And that certainly wouldn't be the case if we hadn't made these modifications. And in fact, if you look at the Fourier transform of this, you can see reflections well out beyond 1 angstrom. And you can actually just barely see the 0.9 angstrom resolution reflection here. So this is very good performance. These higher resolution terms here are heavily damped by that envelope function I showed you on the last slide. However, our goal was to build a 3 angstrom microscope here that could solve structures. And so we were quite happy with this optical performance. So here's the structures. So we said, let's do this now for real. And we knew that the next iterations in hardware development that we were working on were going to take a while. So we said, now's the time to actually show that this thing works in practice. And we got specimens from lots of people. Some of them are the standard test specimens you all know and love, like the ribosome or apoferritin. DPS is a particular favorite of ours in the group because it's like half an apoferritin, so it's a bit smaller, slightly more challenging, and it's very nice for testing things out. But we also got specimens from lots of our colleagues and collaborators at the LMB, in the UK, wider microscopy community, and also around the world. And I'm very grateful to all the folks who gave us specimens to test this out, because they've been very generous with their time and efforts for doing that. But I'm going to talk about 3 of these just as an example to give you a sense of how structure determination works on this microscope. So these 3 specimens, GAP-DH, Lin A, and the last one here, which I clipped off the title on, but anyway, I needed to put a picture of the 2 folks who did all of this here. So these are 3 specimens, or sorry, ALDH1. These 3 specimens were just selected by these 2 students here, Katerina and Daniel, as interesting ones. So, to show that you can actually do not just, test specimens that people had spent, years optimizing and have in their freezers, but actually things that you would do new. So they picked these 3 specimens. We downloaded the genes from AdGene, expressed them with a very simple E. coli and affinity purification, put them on grids, and in 1 week's time, we had all these structures. So, you really can do what I think most people want to do, which is find the structures of these things quite rapidly. And another thing I'll highlight here is that the amount of data collection we did to actually do this is quite small, actually. So all of these were collected in 1 day's time. So the typical day on this microscope is you come in the morning, you've plugged your grid, you put it in the microscope, you have a look, is it bad? You take it back out, you plunge another grid. And, you know, certainly by lunchtime, you can have hopefully 2 or 3 grids in and have a good one, you know, by the end of lunch. And then once you've decided that it's good enough to start collecting data, you just start. And we just started collecting images, you know, immediately. And we didn't, for any of these structures, do more than about 400 movies. And these are 1K by 1K movies, mind you, which, you know, in pure pixel terms, that's equivalent to maybe 10 or 15 4K by 4K micrographs. But if you include the sort of difference in magnification and the difference in performance of DQE, it's maybe something like 100 micrographs. So, you know, on a modern high-end automated microscope, this would take a few minutes to collect if you weren't doing it manually. And all of these were sufficiently high resolution to give us very nice structures and build atomic models into the maps. So these are just the 3 FSCs for those 3 structures. You can see all 3 of them are essentially going beyond Nyquist quite significantly, actually, into the super resolution range. And when you compare the map model FSCs with the half map FSCs, you can see they actually match quite well, meaning that these really are good maps, and you can build models into them quite nicely. And so those were all deposited recently and are in this paper that we published earlier this year. Right, so what else was important in this? I'm going to put in a few more details here because of the particular audience, and one of them is magnification. So and I think this is an important thing possibly to discuss either online or offline in the future, but you know, each one of these structures was collected on a different day by a different person. We had lots of people involved in this, and you know, they may have set up the optics slightly differently. There's no automated software to do anything on this microscope. It's all, you know, aligned manually by hand by users, mainly me, but other people as well. And so occasionally we would have different defocus settings or whatever. And so the magnification did change between different data sets. So it was quite important to get this right. And we've been looking at this recently, and it turns out that I'm pretty sure a lot of the magnifications that have been used for structure determination in the cryo-EM field are probably wrong to some significant degree. And other people have observed this as well, especially Takanori, who from Chora's group, who's now back in Japan, has, you know, really championed the idea that this needs to be sorted out. But we were keen to find a way that you could actually check magnification without having to do an apoferritin structure, for example. And so Josh Dickerson, following on from work from Aaron Leahy, who was in my group formerly and now is in the Netherlands, who started this project, set up to try and do this using just the gold lattice that's in a lot of the grids that we have. In fact, you can use any lattice you want. Gold is convenient because we use it in a lot of the grids we have, and you can actually get very accurate magnification calibration using this lattice as a reference standard. In fact, you can do better than you can with X-ray maps, or at least as good. So, and there's one other just sort of fine detail here. Lots of people use an apoferritin crystal structure, and then they cross-correlate it into a map that's determined at a particular magnification, and then they use that as their absolute pixel size. But this is a slightly dangerous thing to do, because if you, instead of look at apoferritin, you actually look at, say, DPS, where there's lots of crystal structures in the database, you'll find that they have different magnifications. And in fact, they have different sizes. So these are all the different X-ray models in the structures determined by X-ray that we then cross-correlated against our DPS map. And if you take the mean over all of these structures, you do get a value that we think is quite accurate, but you can get this very quickly by just measuring a few images of the gold lattice instead and get to the same degree of accuracy. So we think this might be quite important, and eventually this should be integrated into the software, but it also highlights that there's probably a lot of errors in magnification in the models that are going into the deposition systems, and this is something that we're going to have to deal with as a community as well. Right. What's next for hardware on the microscope? Well, we have a few things in mind. One is a larger detector, which of course we need more than 1K by 1K. This would give us an immediate increase in the signal to noise at 3 angstroms by a significant degree, because we can do this magnification trick that everybody does already with 4K detectors. And we think we can go even further with the CC of the lens, which would give us another significant boost at 3 angstrom resolution and an even larger boost at 2 angstrom resolution. And then I think combined with the 30% reduction in radiation damage, we'd actually have a microscope that would outperform any of the current 300 keV microscopes on the market today. And so there's a lot of efforts that are ongoing to develop new detectors for 100 keV. So hopefully this, in combination with efforts from the microscope companies, will then actually lead to products that we can buy. So commercialization is the key step here, although we would not leave any of these behind, because each of these are factors of 2 that are very significant. So I'll leave this part of the talk with this picture, which is a picture from our lab. This is Ruslan Efremov from Brussels, who many of you may know, and he was coming to visit to see the microscopes. And we have Thermo Fisher Tundra, which is a nice 100 keV microscope developed by them, probably from our encouragement, and which is a very good step in the right direction. And then this is the put together prototype that we had. So we're hoping that soon folks like you or Ruslan or anybody else will have a choice of 100 keV microscopes that will be both cheaper and better than what we have right now at 300 keV. So I'm hoping that's going to be soon. Now, there are a few outstanding problems in single particle cryo-EM, which we're still working on hard, because I think it's clear. I think it's important to make clear to the field that we're not done yet by any stretch of the imagination. And this is sort of the hierarchy of problems that we're interested in working on, because we think we'll get much better models out of cryo-EM if we solve all of these. So the first is movement in the images, which of course we spent a lot of time working on. And the biggest advance there was making these new grids with small holes, which are now commercially available. But that unlocks this idea that you can actually do something about the radiation damage that's incorporated in all the maps that we're imaging now. So even the beautiful, extremely high resolution maps of apoferritin that Hua showed and Holger and Shores and others have done, they all have radiation damage artifacts in them. I'm absolutely certain of this. And we need to deal with that, but you can't deal with that until you deal with the movement in the images. So Jude Short in our group is following on from Katerina's work to develop a piece of software that can extrapolate back to the beginning of the maps using the structure factors. And Alexander Shrytov, who's in Garib Mushidarov's group, is trying to do this using the models. And both of these approaches are very interesting, and I'm excited to see how far we can go with them now that we can actually collect data sets that don't have any movement in them and don't have this downweighting at the beginning. And then once we have that, we actually need to improve the scattering factors that we're using for the model building, which is also still not correct. And Alexander and Hugh Wilson in my group are working on this as well. And then once we've gotten the scattering factors right, we'll get even better models. And then you can actually start looking at chemical changes and redox chemistry and things like this, although we're still not going to get to the doses that you could do with crystallography, probably the sort of 100 kilogray range. But we can get a lot closer than we are now, I think. And then, of course, the biggest opportunity for improving things in single particle cryo-EM right now is specimen preparation, in my mind. And the key to that is to have microscopes that you can walk up and use yourself, because then you can work on the problem with your specimen and not have to rely on some other person to come and fix the problem for you, because we're not in a state where we fix this problem yet. And so eventually we would love to have perfect specimens every time, and then you would be able to automate absolutely everything, but we're just not there yet. And then finally, I think time resolved cryo-EM has a big opportunity, and Anastasia Usach is also at the LMB and has collaborated with many of the folks working on time resolved cryo-EM is here at this meeting as well. So, the future is bright. The structures being determined keep going up and up, and it's quite exciting to be in single particle now. And I think it's going to continue for some time, because there are several orders of magnitude to go in my mind from where we are now. And then in a decade or so, when we come back to this meeting, we can be talking about the 100,000 structures that have been determined by cryo-EM, and not just the tens. So that's great. Right. So I'm going to briefly touch on in situ. I know I've used most of my time here, but what can you see in state-of-the-art tomograms? And this is a state-of-the-art tomogram from the group at Martinsried. And you can see the beautiful mouse retina here and these individual proteins inside the retina, but you can also see the problems with the fib milling techniques and the imaging that we have now. So we've looked at this from a purely theoretical basis, and we started with Richard's 1995 paper where he explained the theory of what's the smallest molecule that you could identify in single particle and possibly solve by single particle. And we know this theory is, in the Richard way, roughly right, because we are reaching the levels that, was there. We've seen, 40, 50 kilodalton proteins now, which are getting solved. So that's quite exciting. And so if you take this theory and extend it as a function of specimen thickness, you can actually look at where tomography is now and where it might be. And it turns out that tomography does have a long way to go. And this either makes you pessimistic or optimistic, depending on your view of the world. For me, it makes me very optimistic because it means that there's lots of improvements that can be made. And in particular, our microscopes today ought to be able to be on this curve so that, say in a 4,000 angstrom thick specimen, you ought to be able to, determine in situ structures of, a few hundred kilodalton proteins. And we definitely cannot do this, or certainly not do this reliably today. And the reason we can't do it reliably are these four things, I think, at least. The thinning technology needs vast improvements, plasma fibs and fibs and, Symobis. These are all interesting techniques, but they all have lots of problems and they need to be worked on. We need to do the things that we've done in single particle already, including reducing the charging and movement of the specimens. We need improved software and algorithms for actually doing these alignments and reconstructions. And we certainly need better detectors that are faster and bigger than what we have now. And if you could do that, then if you can actually get back some of the inelastic electrons, which Pei is going to give a talk shortly, so I'm not going to talk much about this, but then you could push this curve even further down. And if you could do that in conjunction with a phase plate, which is, another exciting technology that's an idea that's been around for a long time, but there are lots of new developments in this area, particularly at Berkeley in their development of the laser phase plate. If you could combine these two technologies, then this pushes this down even further. And if you could reduce the radiation damage by cooling to lower temperatures and not have other problems, then you could really get down into the range where we could see all of the sub 100 kilodalton proteins inside of a cell, even in a fairly thick specimen. So that would be very exciting times indeed. And so I hope that's what we're going to be talking about at the 20th anniversary of the CCP-EM meeting. Right, I'm going to skip that because of time. So I'm hoping, or at least, my impression of how the field is going to go is that there's actually going to be a divergence between in situ imaging and single particle imaging in terms of the technology and of the microscopes hardware wise. So this is what we really want, the simple 100 keV 2 angstrom cryomicroscope that any structural biology group or small department can buy for themselves and do cryo-EM very effectively. And then they can always come to the larger facilities where there's more expertise and more automation and go as high as the technology will let them in terms of resolution and data collection. But that is the key part of the whole process. And then, you can always have a high-end automated version of this that is very easy to use and enjoyable. But the in situ world, I think the dust has not settled on how this technology should look and what we need actually. So this just needs a lot more work on our part from the academic side to make this happen. So it's still a research project at this point. And, it could be that STEM could be involved here because, it's not subject to the same chromatic aberration that we're limited by in TEM. However, it's got lots of problems of its own. And Karsten's going to talk about their efforts there, who's probably gone the furthest on this so far. But, what exactly this instrument looks like, I'm sure it will not look like what we're buying today in 10 years' time. But exactly what it looks like, we're still going to have to find out. Right, so I'll stop there and thank all the people who are involved in, especially the 100 keV project. And I just want to mention first I'll especially mention Greg McMullen, who has led this project and really spearheaded everything involved in making this microscope work and continues to do so. He's very notoriously difficult to take a photograph of. He happened to be taking the pole piece out of this microscope at this time. And so then immediately Richard and I realized we could get a picture of him. So this is the picture. And I also want to thank all the folks, the funding folks who helped us get started, especially a bunch of the pharma companies contributed to us before we could even get a Wellcome Trust grant to get this project off the ground. And that was essential. I'll also mention that the LMB EM facility is expanding and is keen to hire somebody soon. So you could be a part of that team if you're interested in. And if you'll indulge me with one more slide, since we're going to do a discussion immediately after this, I thought I would put up a metaphor for you. So this is a picture of a book from the ecology world. And many of you may know that, ants and trees often have a very interesting symbiotic relationship. And while I was having lunch with Hugh yesterday, we sort of discussed the idea that actually the relationship between the commercial world and the academic world of cryo-EM is not so different from the relationship between ants and trees. So it can be symbiotic. The tree can benefit enormously from the fact that the ants bring in nutrients and things from further away, and they can actually sting predators that come in, and the tree can grow much larger than it would otherwise do if it didn't have the ants. But it can also turn into a parasitic relationship, because if the ants get too greedy, they start eating all the little shoots and buds on the tree, and then the tree actually ends up dying. And so I'm hoping we're going to keep the symbiotic relationship going. It is supposed to be funny. You can laugh. It's allowed. And so, and I think that, CCP-EM is going to be the key to keeping this ecosystem healthy over the long term, because it can serve the role of keeping, this ecological system in proper balance. So I'm very thrilled that CCP-EM has come so far. The people who started it should be extremely proud. And I just want to say happy birthday to CCP-EM, because it's a fantastic thing, and I'm really happy to be a part of it. So I'll stop there.